In Boltzmann's theory of statistical mechanics, the three types of molecular motion, translation, rotation, and vibration, and electronic levels, can be described in terms of microscopic energy states. Each state has an energy, E sub I. Indeed, each of these types of motion is described by a wave equation in quantum mechanics, and the solutions form sets of energy levels precisely as predicted by Boltzmann 20 years before the wave equation was discovered. The Bohr atom, published in 1913, was the first example of electronic energy levels. Energy levels have been part of your chemical education from the beginning. It is not difficult for us today to assimilate what Boltzmann proposed, but during his lifetime, there was no explanation for the levels, and many scientists refused to accept the idea and even ridiculed it. Here we see the prescription for calculation of the average energy. The angle brackets mean average. The average energy is the sum of the probability of each state times the energy for that state. Beyond energy levels, Boltzmann proposed that the relative population, and therefore probability, of any two states, M and N, was given by the exponential of the energy difference between them divided by kBt. Kb is Boltzmann's constant. When Kb is multiplied by Avogadro's number, we obtain R, the universal gas constant. Note that the form of this relationship is analogous to an equilibrium constant, which of course would be equal to e to the minus delta G naught over RT. There is no entropy for a microscopic system, so the energy of a single level replaces the free energy. Boltzmann's relationship is to a molecule what the Gibbs free energy relationship is to a mole. The probability, capital P, of the ith state is the population P of that state divided by the populations of all states in the system. Any property of state I, call it M sub I, can be averaged in the same way as energy. You take the sum of P sub I, M sub I. The sum of all populations in the denominator is also called the partition function. It determines the partitioning of probability among the various states. The definition of a partition function permits us to write a compact expression for the probability. The standard nomenclature is Q for the partition function. Using this definition, the probability of big P sub I is the population, little p sub I, divided by Q. To illustrate the partition function, probability, and average energy, we consider a two-level system. The lower energy level has an energy of 0, and the upper energy level an energy E. Since e to the 0 is 1, the total population is given by 1 plus the exponential term e to the minus capital E over kBt. The average energy is also shown here. At absolute 0, the energy is 0, because all the population is in the lower state, which has an energy of 0. At infinite temperature, the population of both states is 1/2. The population is equally distributed between the states. There are many problems that reduce to a two-level system. For example, NMR of spin 1/2, electronic transitions from a HOMO to a LUMO, and so on. For each type of kinetic motion, translation, vibration, or rotation, there is a specific form of the partition function. The harmonic oscillator energy levels form an equally spaced set of energy levels, an energy ladder. Boltzmann proposed this without a rigorous justification, other than that it works. By the 1920s, it was possible to solve the quantum mechanical harmonic oscillator and show that the energy levels are indeed an infinite set of equally spaced energy levels, and that spacing is h nu. Since the levels form an infinite set, the partition function is an infinite sum of exponential terms. that decrease as the energy level increases. It is not convenient to use formulae that have an infinite series in them. We can make a substitution that permits us to write the infinite series as a geometric series. The infinite geometric series can then be written in closed form using the procedure shown on this slide. The trick is to multiply the series by x, and then compare that to the original series to show that q minus 1 equals xq. Then we solve for q. In the infinite energy ladder, there is also an infinite number of probabilities. That infinite series can be written as the derivative of q with respect to 1 over kBt. When the derivative of q is divided by q, it is evident that one simple closed form expression can be used to derive the average energy in statistical mechanics. It is shown here. It is a bit surprising that the infinite energy ladder has the same expression for the average energy as a two-level system. Although we did not write the two-level system in the compact form obtained by multiplying both numerator and denominator by e to the h nu over kBt, you can check that this is possible for the two-level system. One important check on the consistency of this result is to see that it gives the classical result in the high temperature limit. The exponential term in the denominator can be expanded in a Taylor series when h nu is much less than kBt, which is the definition of the high temperature limit. The ones cancel, and the first surviving term is energy E over kBt. When this is inserted into the average energy, the energy does indeed become kBt.